From blast waves to blood waves, applying viscoplastic energy model, VMT, across engineering and medicine. Number 1351, VMT Sharp 698, September 8, 2025. Gerald C Hsu, EclaireMD Foundation. Category, Methodology. Introduction. Engineering and medicine often seem like separate worlds. One studies steel, concrete, and impact the other studies organs, blood, and disease. Yet both deal with the same reality, systems under severe stress, that respond in nonlinear, plastic, and irreversible ways. My PhD advisor at MIT, Professor Norman Jones, dedicated his career to studying structural responses under extreme conditions such as blasts, collisions, and sudden impacts. He showed that under these dynamic loads, materials behave very differently from the neat, elastic assumptions of standard engineering design. His work demonstrated that plastic deformation, time, dependence, and cumulative energy absorption are central to understanding real structural failures. 4 decades later, I have carried this same logic into biomedicine. Through my self-collected health data and medical crises, 5 heart attacks, kidney failure, neuropathy, retinopathy, and a recent hemorrhagic stroke, I recognize that human diseases behave just like those extreme engineering systems. They are nonlinear, time-dependent, and irreversible. Traditional medical research, like conventional engineering's linear assumptions and design, often misses the crucial truths hidden in extreme cases. The engineering perspective. Professor Jones's research proved that ordinary design equations fail when structures face blasts or strong collisions. For example, a bridge designed for average traffic loads may collapse under a single high-speed impact. A protective wall that seems adequate under static pressure may fail instantly when exposed to a dynamic blast wave. In such cases, the system is not governed by averages, but by energy extremes, rate effects, and irreversible plastic deformation. These insights could only be reached through advanced modeling of dynamic plasticity, not by conventional static equilibrium methods. The medical perspective. My medical journey mirrors this logic. For years, research doctors and public health studies focused on averages, mean blood pressure, hemoglobin A1C, BMI, and so on. But these averages concealed the true dynamic energies driving many mortality diseases. In my personal case, on June 21, 2025, a single blood pressure surge to 175 mm of mercury, combined with aged and stiffened vessels, caused my hemorrhagic stroke near the brainstem. This was the medical equivalent of a sudden blast load. Acute, high-frequency energy that ruptured a weakened vessel. Over decades, chronic elevated glucose acted like a slow, but relentless plastic. Its low-frequency energy accumulated, silently, damaging many of my organs until diabetes, kidney disease, neuropathy, retinopathy, and cardiovascular conditions emerged. Traditional public health methods might conclude that average blood pressure, or average glucose, is manageable. But just as average design loads cannot predict structural collapse under blast, average clinical metrics cannot predict when a patient will suffer a catastrophic stroke or heart attack. Viscoplastic energy theory is the bridge. Viscoplastic medicine theory, VMT, energy model, provides the common language to unify these two fields. Stressors, in engineering, loads from impacts or blasts. In medicine, glucose, blood pressure, visceral fat, and lifestyle factors such as overeating, inactivity, poor sleep, and chronic emotional stress. Strain, in engineering, permanent structural deformation. In medicine, irreversible damage to tissues and organs, leading to deadly disease. Energy, in both fields, the cumulative interaction of stress and strain over time, which determines system failure. The critical insight is that failure is governed not by averages, but by cumulative and extreme energies. Whether in a steel plate deformed by collision or a blood vessel ruptured by hypertension, the same principle applies. Why statistics and conventional design fall short. In engineering, static safety factors cannot capture dynamic collapse mechanisms. In medicine, population-level averages cannot guide treatment for individuals facing extreme spikes or long-term accumulation. Professor Jones's work showed that structural safety requires nonlinear, time-dependent analysis. My medical research shows that patient safety requires the same physics-based modeling of cumulative and extreme energies, not blind reliance on averages. A stroke case study revisited. Using VMT, my stroke can be explained in the same terms as a structural blast failure, acute high-frequency load, blood pressure spike, triggered by emotional stress and anger. Like a blast wave, the surge exceeded vessel capacity and caused rupture. Chronic low-frequency load, glucose, like fatigue, loading, glucose damage accumulated invisibly until organs weakened and failed. No traditional statistical model could integrate these dual processes. VMT can, seamlessly. Conclusion. From MIT classrooms in 1972 to my hospital bed in 2025, one truth has remained constant. life, whether in steel and concrete structures or in tissues and organs, is nonlinear, dynamic, plastic, and irreversible. Normal equations and averages cannot capture this. Professor Jones pioneered the study of engineering extremities, structures under blasts, collisions, and sudden impacts. Inspired by his mentorship, I extended the same viscoplastic principles into medicine. For example, studying glucose waves and blood pressure waves as biophysical loads. I believe I may be the only research scientist applying viscoplastic energy theory to medicine. Yet the results are clear. VMT explains why small stresses from long time hyperglycemia accumulate, why hypertension spikes kill, and why averages deceive. It provides a framework to prevent disease, just as dynamic plasticity provides a framework to prevent structural collapse. In this way, Professor Jones's legacy in engineering lives on. In my biomedical research, what began as classroom lessons on blast loads in Cambridge in 1972, now continues as a framework to save human lives in California in 2025. And I teaching AI beyond averages in biomedical research. In the past 2 to 3 years, I have come to see my work as a partnership between NI, natural intelligence, human brains, and AI, artificial intelligence, computers. Many assume AI is the teacher and humans the users. But in my case, the flow often goes the other way. I use my experience, creativity, intuition, even emotions, to guide AI systems toward a deeper understanding of complex biomedical problems. Using the viscoplastic framework, early or even present AI systems, built on millions of published statistical medical papers, tended to rely on averages. They flattened data, reduced variation, and highlighted correlations. This is useful for population studies, but it fails to capture the real drivers of chronic disease. A patient does not suffer a stroke because of average blood pressure over a year. They suffer because of one catastrophic surge, a hidden outlier. Just as Professor Jones showed in engineering, that structures collapse under blasts, not average loads, I have seen the same in medicine. This is where NI teaching AI becomes powerful. My NI comes from my IQ from my parents, in combination with 4 decades of training in mathematics, physics, engineering, business management, psychology and medicine. I can see that a stress-strain curve in engineering is directly analogous to glucose and blood pressure dynamics in the human body. I can explain why nonlinear, plastic, and irreversible processes matter more than linear averages. AI, for its part, gives me rich contents and fast speed. It can generate diagrams, summarize datasets, and translate research. But without NI, these outputs remain superficial without depth and feelings. By teaching and correcting AI systems, refining drafts, and pushing it closer to biomedical truth, felt by human heart and brain, I am training several AI tools, especially ChatGPT, to move beyond averages into extremes, outliers, and cumulative energy, the essence of applying VMT in medicine. My research has therefore become more than the study of medicine. It is also a continuous experiment in human-machine collaboration, which I have pursued more than 3 decades in my professional career. NI guides AI, AI amplifies NI, and together they create something neither could achieve alone. Appendix, VMT statement. The viscoplastic energy theory, VMT, is a math physics framework that models disease as cumulative, nonlinear, time-dependent, and irreversible, the same principles that govern material failure under stress. It provides a dynamic systems approach for understanding health outcomes, beyond the limits of statistics. For details, please search Health Talk with EclaireMD on YouTube. Disclaimer: this content is for educational reference only and not medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be edited or republished as your own.